So far we talked about single bodies either emitting radiation or absorbing radiation, okay? But what if we are looking at two different bodies? For example, one body is emitting and the other body is absorbing, or both bodies are absorbing radiation. So what is the relation? So for example, if we now look at two bodies, so for example, we have body 1 and we have body 2, okay? So both bodies are above epsilon, above the absolute zero temperature. It means that both of these bodies are actually emitting the radiation. But at the same time, both of these bodies are also absorbing radiation from each other, okay? So if we now look at two bodies, body 1 and body 2, with infinite areas, it means that they are very large in area, so we don't have to worry about the area. And if they are separated by vacuum, so we can calculate the heat flux by this equation, so that the Q dot, that is the heat flux by radiation, is equal to the EB1, that is the energy, for example, emitted by one object minus the energy emitted by the second object. So this Q gives us the energy exchange between these two bodies. And if you remember from the previous slides, that EB is equal to sigma Ts, okay, times to the raised to the power 4. And if it is a gray body, then we have to multiply it with this term here, epsilon, as well, because then it converts the black body into a real body by using epsilon. Okay, so now let's imagine that these two bodies are actually not infinite in area, but they are of finite size, because most of the bodies that we deal with are finite size, okay, in engineering or in common life. So they all have certain surface areas. So in that case, we can calculate what is the radiation, for example, exchange between the two, or the energy exchange between the two. In this case, we can write the rate of heat transfer. So this is not the flux anymore. This is the rate of heat transfer for example, you have an object that has an area A1, and then you have another object that has an area A2. Okay, so the heat energy that is actually this emitted from object A1 and is being received by object 2. So we can write this heat energy as F12, that is a shape factor, and I will explain in a minute what that shape factor means, times sigma, that is the Boltzmann constant, times the area of the emitter A1, that is this surface here, this object here, times the temperature difference between the two objects raised to the power 4. Okay, so Ts1 is the temperature of the object A, and Ts2 is the temperature of the object 2. Okay, so now this factor F12, so this factor F12, what it means that, for example, if you have an object here, okay, and then you have the other object that is, let's say, slightly smaller or of the same size. So all the radiation that is emitted by this object is not going to be absorbed by the second object, okay, because it is only going to be absorbed the amount of energy that is going to fall on it. So if, for example, this energy is not going to touch it, it's not going to absorb it. Okay, so this factor 1, 2 defines this relation, that to what degree the radiation is emitting by the first object is actually falling on the second object and is being absorbed. Okay, so the shape factor depends only on the specific geometry of the emitter and the collection surface. Okay, and it is defined as, for example, the fraction of the radiant energy that is diffused from one surface element and strikes the other surface element directly without any intervening for example, disturbances. Okay, so this factor is represented as 1, 2. So it means that the radiation shape factor is showing that the surface A1 is emitting energy and it is being absorbed by the surface A2. Okay, and this equation itself defines that, for example, the heat transfer rate from surface at a temperature T1 and area A1 to a temperature T2 to area A2. And this relation between A1 and A2 is actually what is represented by this shape factor here. Okay, so the rest of the equation is very simple because this is actually the same equation that is here. So we know that EB is equal to sigma times T raised to the power 4. Okay, and raised to the power 4. And so if you put the value in this equation and then multiply by the area, that is A1 here, so you have this sigma times A1, and then because you have two temperatures, TS1, TS2 raised to the power 4. So this is exactly the same equation. You just have put the value of this sigma times T raised to the power 4. Okay, and then we have to multiply this whole equation with F12 to calculate that what part of the energy that is being emitted by surface 1 is actually being absorbed by surface 2. Okay, so that's what I explained in the previous slide, that what F21 factor F12 is. And so it is also called as coupling factor, or it is also called as configuration factor, view factor. There are a lot of names for it, but they all explain the same thing. And mathematically, we can look at these factors as given by this formulation here. And as you can see that these are quite complex, but these are purely geometrical terms. Okay. And we are not going into detail of this factor 1, 2. So if, for example, if you in exam, if you have a question that requires the value of f factor 1, 2, the value will be given to you guys. Okay, so you don't have to calculate factor f1, 2, but you do need to understand that what is the relation between these different areas. For example, the area of the receiver and the area of the emitter as well. Okay. So now, in the previous case, we looked at, for example, for the black bodies, but if we have a gray body, then we have to multiply that equation by epsilon. Okay, so that equation will be, we have to account for what is the emissivity of the first object. Okay, and other thing that is important here to notice that we also removed, for example, the factor 1, 2, or the shape factor. And the reason is that if we assume that one of the body is black body, or it has a very large surface area, so we can ignore the shape factor. So for example, you have this is the sky, and this is or the space around us, and this is the earth. Okay, so all the energy is coming from the sun. Okay, so now we can ignore the shape factor for two reasons. Because one, we can assume that that sun is a black body. Okay, that is one option. And the second one is that we can also ignore the shape factor because all the energy that is emitted by the sun actually is because it is surrounded around us, so we can assume that all the energy that is emitted by the sun is actually receiving by the earth. Okay, so we can ignore the shape factor here, and then we have a much more simplified equation. So that is a simplification that we normally use to get out of the tricky situations. So just by assuming that one body is black body or has a very large surface area, we can ignore the shape factors. Okay. So that is all for this part and for this lecture. So as I said, that now you should be able to understand what is heat transfer and use the governing equations of Stephen Boltzmann law and Planck's law and Wien's displacement law to calculate different parameters of radiation heat transfer. And also you should be able to understand or calculate what is the relation between the heat transfer between two objects in a closed system, and how we can actually calculate the heat exchange between the two units or two objects. Thank you for your time, and see you in the next lecture.